Good morning. I think we can start our session. Yes, thank you for confirming. Okay, that's what we have. We do have lesson 6 this week, and we have 2 sections to cover, 6.1 and 6.6. That means we are still in chapter 6. I listed all of the section from chapter 6, but I think section 6.2, 3, and 4, we did talk about the logarithmic and exponential functions. We know the derivatives. And yeah, we know the behavior of the function, we know the derivatives. That means what we do have for today, we will talk about the inverse function in general, the derivative of the inverse function, okay? And tomorrow we will talk about the derivative of the trigonometric inverse functions, okay? And I think section 6.8 will wait for us until Math 141. Okay, that means it is part of the calculus course, but we will talk about this next semester if you're planning to take Math 141. Okay, that means 6.1. Let's start. I do have few information about the logarithmic and exponential, and then just the inverse function. I was just making some notes about the chapter. And as I said, the L'Hopital rule will be Math 141 and yeah, inverse function. You may pause the video and read this information. Okay, that means we know in general, we know the algebra part for the inverse function. I'm assuming. That means I will go through just the algebra part, and then we will focus on calculus. And that's mean what we have. We do just the definition of the function. Of course, that was lesson 1. That was week 1. We know the definition of the function. Yeah. Function arises whenever one quantity depends on another. We have a few ways to define the function. We have a few types of the function: polynomials, piecewise defined function like absolute value or step function, rational functions, algebraic function, which is just like the combination of all of the algebraic operations: addition, subtraction, division, taking the square root, taking the cube root, and so on. Trigonometric function and its inverse, and exponential and logarithmic. That means trigonometric functions, exponential and logarithmic, they are not algebraic functions because we don't really, they are not defined in the algebraic way. They have its own specific definition. Okay, and just looking at these graphs, I think you saw this in lesson 1, but just really quickly because I would like to define the inverse function. Can you tell me which graph is not a function? A, B, C, or D. Of course, I even draw the tool that we're using. That means that graph A represent a function or not really? A and B are not a function. Thank you, Kevin. Thank you, Noah. Thank you, Chuck. Yes, because we can see the tool what we're using is a vertical line test. When we draw a vertical line, we only expect one output. For one single X, we have one unique output. If 2 dots, if we see 2 intersections, that's some kind of relation, but not a function. Okay, that we do have a vertical line test. Okay, now I have the answer. That means inverse functions. Yeah. The question is, how can we define an inverse function? Does every function has an inverse? Okay? And when the function has an inverse, if has the inverse, that means what is important. If we do have a function must have a special property. Okay? And the special property, we know that is 1-to-1, okay? Which means if I use 1x, okay, I supposed to have, of course, one y value. However, if I choose another x, I have to have one corresponding y value, but I can't use the same y. Yeah? Like, for example, I can draw, and we will talk tomorrow, I can draw a sine function. Okay, that's sine. And we do have some values, 3 pi over 2, pi over 2. And this is 1, this is negative 1. And we know it's periodic function. That means, what do you think? Is the sine curve, sine function, 1-to-1 function? It's not, because what's happened, we can see for pi over 2, we have the value 1. For 5 pi over 2, like every 2 pi, we will have the same value. That means we will have infinitely many x values that the corresponding y is 1. That means this is not 1, it's like used few times. It's still a function, but it's not 1-to-1. That's what we have to do. We have to have 1-to-1 function in terms, I mean, with respect to the inverse. Okay, that means, let's see, I do have a definition. Okay, that we can see the function f is called 1-to-1 function if it never takes the same value twice. Yeah, that means one value cannot be used twice. Wherever we have different x's, we should have different y values. And we do have a test, which is the kind of opposite, is the horizontal line test. When you see the function, we may draw a horizontal line, and horizontal line should intersect the curve only once. Then it's 1-to-1. Yeah? But when we have, like, for example, my function at the bottom, the blue curve, it's not 1-to-1, because we see two intersection, which means the same level, the same height, the same y value is used twice. It's still a function, yeah, but it's not 1-to-1. For example, like when we, like, because we can see just the behavior of the function, like we can see function is like increasing. Yeah, let's use a little bit of this. The blue curve, yeah, we can see it's increasing, and it's attaining some kind of like a highest point, okay, and then it's decreasing. Yeah, that means you may like just geometry, like from the geometrical point of view, when we see this behavior that is like the curve is increasing and then is decreasing, like, oh, let's say this way, I will be climbing the hill, right? That means I will have at some point, I will reach a certain height, but then coming back from that hill, I will also reach the same height. Yeah, that means I use the same height twice. That means this behavior, this curve, they will be never 1-to-1. But when we will have a function that is strictly increasing, like we know strictly increasing means on the entire interval, on the entire domain, it's just increasing. Do you think this function will be 1-to-1? I can draw maybe somewhere. Yeah, because we will not have this highest point and then the way back. That means I will, like, for example, this curve, y, x. Yeah, let's say it's like it's strictly increasing. Okay, that means we will never reach the highest point and getting back. We will always have different high. Of course, it's increasing. That means the height will be bigger and bigger. The level, the y values are getting bigger and bigger, but never coming down. Yeah? That means when a function is, it's important information. When function is only, which we will call strictly increasing, it's always 1-to-1. Or the opposite. Let me. If the function is strictly decreasing. Okay, the same situation. The values, the y values are always getting smaller and smaller, and we will never like attain like the lowest point, and we will not get back to reach the same value. Okay? That means strictly increasing and strictly decreasing, it's a good like tool to determine whether the function is one-to-one or not. Okay. Yeah, a little bit of calculus. Okay, maybe we, since we're talking about strictly increasing, strictly decreasing, when a function is increasing, we will talk a little bit closer to this property in chapter 3, which will be next week. But I think you definitely know this. When a function is increasing, okay, can you tell me what will be the value of the slope of the tangent line? Will be positive or negative on the entire domain? Of course, positive, right? Because slope of the curve, I can say, or slope of the tangent line, it will be positive. Always on the entire domain will be positive. Since the slope is positive, how can we define slope in the calculus way? Slope of the tangent. What is the slope of the tangent? How the slope of the tangent line is defined? Do we remember? It's but using some calculus terminology, derivatives, right? Yes, rise over run, yeah, rise over run, but I mean slope as a derivative of the function, always positive, or slope as a derivative, slope of the tangent, of course, or the curve, the same, negative. Okay, that means that's important. Okay, that's just to double check. Because before we do something with the function, of course, we're thinking in terms of the inverse, we have to make sure that the function is one-to-one. But if we check if the function is strictly increasing or strictly decreasing, it's definitely one-to-one. And how we can check? We can check through the derivative. Derivative must be positive, or only negative. Then that's the proof. Okay. That's we know one-to-one property, we know how to prove it. And then I have two functions. This is still just algebra. Of course, function x cubed, it's one-to-one. Function x squared is not one-to-one. Yeah, because, for example, for the value for -2 and for +2, I will have the same level, the same height, the same value of the function. And of course, when I square two numbers, positive or negative, the same magnitude, I will get the same output. When I cube two numbers, I will never get the same number back. Yeah, okay, that's we know. But actually, let's maybe look at this x squared, because x squared is quite nice function, our good friend. Of course, it's not one-to-one, then we have to say this function doesn't have inverse, because if function is not one-to-one, we do not have the inverse. But what do you think? Because the mathematician, they will not leave the nice function x squared like that. Do you think we can, looking at this parabola, can we maybe do something and make this function one-to-one? We can, yes, thank you, Matt. We can limit the domain, we can restrict the domain, which means we can take just part of this blue parabola. And for example, I can take my function x squared only on the interval from 0 to infinity. That means from 0 to infinity. And what do you think? Is this part one-to-one? Just kind of like one branch? Yes. That means that's what we can do. We can have the same formula and we can restrict the domain. We can look at only this interval. And then, of course, we will do the next steps to get the inverse and maybe the derivative. We will see. Okay, but please remember, and especially, you saw I just draw the sine curve. And tomorrow we will talk about the trigonometric inverse function. And trigonometric functions are periodic functions. They are not one-to-one. That means what we will do to make to have one-to-one sine, cosine, or tangent curve, we will cut. We will not take the entire wave. We will restrict the domain. Okay, that means that's the tool. That's the way to manage not one. That means basically every function we can make one-to-one. Yeah, but we have to remember where we're looking at. Okay, we're good with this. And then just some still algebra. Definition of the inverse. That means this is just the basic notation. Yeah? We probably remember f of x equals to y, then we interchanging x and y's, but that's the way to indicate this. If f of x is y, then x is equal to inverse f of y. Okay, that means that's the, and we simply interchanging x and y, which means domain of the original function will become range of the inverse and range will become domain. Yeah? The only thing is, please remember this notation, okay, f to the inverse is like, it's not an exponent. Okay, that means it doesn't mean that it's like function f taken to the power of -1. That means this is not, that's not 1 over. If we would like to have the reciprocal, I will rewrite like that. Yeah, the entire function f of x to the power of -1, then it's 1 over. But when we have the -1 placed like between, like that, this is just the notation. Unfortunately, is that the notation? I don't know, but we probably will get used to, and you will not make the mistake. Okay, but please remember this. Okay, let's keep working. Yeah, that's just the definition. Again, I just wrote the other way. The inverse of f inverse of x equals to y, then f of y equals to x. That means, can you tell me these numbers? If f of x is 3, then f inverse at 3 is, what will be this answer with respect to the information? Yeah, we just in x. Thank you. Okay, if f of x is 1/2, then f inverse at 1/2 is also x, of course. And now, if f inverse at 5 is 6, then what is the value at 6? Of course, 5. Looks trivial, right? Yeah, but it's important because we will always interchange. Yeah? And this will be one of the formula that we will use in our calculus question, okay, in a minute. But please remember, because it's so trivial, I mean, probably when we know the solution to the math question, it's always trivial. When we don't know, yeah, it seems too impossible to solve it. I know that. Okay, but I like it when you find this easy. I really like it. Okay, let's keep working. Okay, that means this is still algebra. How can we find an inverse? We will have an equation, and as mentioned before, we have to interchange x and y and solve for the new y in terms of x, and the new y will be the inverse. Okay, we can see. And also one nice property, when we put a function and its inverse at the same xy plane, they will be always symmetric with respect to that yellow line, which is y equals to x, because we interchanging. That means they will make this nice symmetry. And it's nice property. I can tell you that, like, mathematician, they will probably question a little bit, like, how we can put a function and its inverse like to the same xy plane, because we interchanging the domain and range. That means it's some, if we think a little bit deeper, could be confusing. But if we think just, yeah, like xy, we have new function, like the inverse will be completely new function. We can treat domain and range as a new function, then this is the property. Okay. And we do have a cancellation equation. equations, which means when we will make the composition of a function and its inverse. Okay, function and its inverse, we will always get the final answer, the final output will be x. Okay? We can like think this way: when I have x and when I add 5 and then I subtract 5, because addition, subtraction are the inverse operations, then I will get x. Or if I will take x and divide by 5 and then multiply by 5, I still get x. Yeah? And inverse function for x cubed, of course, is cube root of x. Okay? And when I make the composition, the compound function, cube root of its inverse, cube root of x cubed, of course, is x. Or the other way, I will cube the inverse. I will cube root of x. Of course, it's x. Yeah, that's what we can see. It's nice, really nice property. Yeah, for some other thing. Okay, it's me now. Calculus of the inverse. That's when we know function must be one-to-one. If it's not one-to-one, we may restrict the domain. Okay, that's what we will try to do. Let's see, just a few theoretical parts. That means, first of all, if the function is one-to-one and continuous function, of course, we don't want to have any discontinuity. Nice and continuous function, one-to-one and continuous, then we know that the inverse, we can like find a formula, we can place both of them in one xy plane and they will be like nice and symmetric, the mirror image with respect to y equals to x. But what is my point? If the function is one-to-one and continuous function, then it's the inverse is also one-to-one and continuous. Yeah, that means that's the, especially the continuous. If the function is continuous, then the inverse must be continuous because it's just the mirror image. Okay, and now the same, that we have continuity, right? Because if function is not continuous, we can't really take the derivative at that point. And then the same thing. If the function is one-to-one and differentiable, which means, of course, continuous and also no sharp corners, nice and smooth curve. That means one-to-one, continuous, of course, and smooth, differentiable. Then the inverse is also holds the same property. Yeah? If f is one-to-one differentiable function defined on an interval, then its inverse function, f inverse, is also differentiable. Okay? Except where the tangent is vertical, because it's also nice and smooth. Yeah? But we will be careful to look at, we will exclude that point. Okay? But it's definitely, if the function is differentiable, then the inverse is. Okay, that's mean now what we can do. We can think about the inverse function and try to find the derivative. And now I have to probably clarify something, because you may think this way, function x cubed, okay, its inverse, maybe I can write as a f of x, and the new function, which is an inverse, is cube root of x. Yeah, that means this is inverse, or the other way, x cubed will be the inverse for cube root of x. That means I have my function x cubed, I did my algebra and I found the formula for the inverse. And now if this is cube root of x, I think we have no problem to differentiate. Yeah, we can use power rule, we know even chain rule, now just the x to the power of 1/3, and we can follow the formulas. Of course, yeah, that's not a problem. But what is the point of this section of the chapter 6? We would like to find a derivative of the inverse function at one point without having a formula of the inverse. Okay, I will repeat one more time. That means I would like, we can see this question mark. Everybody can find the formula. Everybody can fill out that gap, question mark. But now we have to imagine that we still have to find out this question mark, not having the explicit formula for the inverse. Okay, because what is the problem is sometimes it's quite complicated to find the inverse. And we can always ask calculators, we can always ask computers, but it's not easy to find the inverse, depends on the function. And then when we can't find the inverse, but we still want to have some information about the inverse, for example, the derivative at certain point. Okay, that's the point. And let's see how we can do. Okay, derivative of the inverse function. What I will do, I will get some equation, and I think I picked this one of the cancellation equation. Function f, composition, compound with its inverse will give me x. That's what I have. I have the inverse inside. And I think I can take this equation and use implicit differentiation to differentiate this, because I'm looking, what we're looking for? We're looking for the inverse derivative, inverse prime of x. Okay, that's what I'm looking for. I'm looking for the formula of the derivative of the inverse. Okay, we can see inverse prime. And I do have that inverse, and you may probably think applying the chain rule, we will get that part. Okay, that means let's do it. I will differentiate the equation like it is with respect to x. On the right hand side, I have just x, which is derivative of x is 1, but now we have to be careful. Derivative on the left hand side, derivative of the outer function times derivative of the inner function. So we remember, let's see, f prime, and still the input is the original input, f inverse, times derivative of the inner function. Now we can see just the chain rule. And this is the part that I'm looking for. And let's just divide, and this is the final formula. Let's read this. The inverse prime, which is derivative of the inverse prime of x equals to 1 over f prime inverse. Yeah, I wanted to switch this. F inverse prime equals to 1 over f prime inverse. We can see we kind of like, I'm just trying to read quite like make this accessible. Okay, that's we can see inverse prime, prime inverse, 1 over. Okay, let's see my summary slide. That means that's the second formula for this section. We know the first one. That means we just need these two formulas and you can solve every question in this section. If function f is 1-to-1, differentiable function, with inverse function f inverse and of course the derivative of the inverse at the certain a value is different than 0 because we have this value in the denominator. Then the inverse function is differentiable at a, and it's defined like this. That means you can see I did remove x because I wanted to be more specific. I just defined the derivative of the inverse at a, at the certain number. Okay, that means f inverse prime at a is equal to 1 over f prime inverse at a. Just switching. Okay, that means we have to. Okay, if you will solve the homework question, a few questions from the suggested homework from the section, you will probably like get used to this formula. Okay, let's just solve a question. If the function is defined as a 1 over x minus 1, and we do have domain, okay, that's mean I don't know if this function is 1-to-1, but we do have restricted domain. And since we're asking to calculate the inverse, I'm assuming that it is 1-to-1, but we will still prove it. Okay, function again 1 over x minus 1. and calculate, okay, calculate the derivative of the inverse at 2. Okay. That means, again, you will probably think, oh, I can quickly find the formula for the derivative. Oh no, for the inverse, and then differentiate and substitute 2. Yes, we can do this. And I think for this formula, we can even do this way. But you will see my next question, we will be not able to do this way. Okay. Okay, let's do the way that we just learned. And this is supposed to be exercise 1. Okay. Oh no, no. Exercise, because it's first calculus. No. I did have the previous one, was the algebra exercise. Okay. That means, first of all, what we can do, without computing the formula for the inverse and then derivative, we can still calculate this. Okay, we can still get the derivative of the inverse at 2. And we will use, okay, I will just because I typed the solution. That means, since we're talking about the inverse, it would be nice to prove that function is 1-to-1. And as I said, we will probably assume that it is, but let's see, I kind of typed the hint. We can try to find the derivative, and we will look at the formula of the derivative, and I just actually typed the conclusion. The derivative is always less than 0, is always negative, which means function is strictly decreasing. But let's find the derivative. That means this exercise is, I'm not looking for the inverse, I'm just looking for the derivative. I can rewrite this function as a x minus 1 to the negative 1, and then derivative will be negative 1, x minus 1 to the negative 2, times derivative of the inner function, which is 1. Okay, no problem. I don't have to put 1. Negative 1, x minus 1 squared. Okay. We can nicely see we have denominator squared, always positive, and we have negative 1 on the top. That means this quantity, whatever value we will substitute instead of x, this expression, it's always negative because of that negative 1. If it's always negative, that's derivative. The original function is always decreasing, strictly decreasing. Okay, that means I can check function is definitely 1-to-1. We don't even have to restrict the domain. But because we don't have x equals to 1, we have discontinuity. That's the reason that I restricted the domain. Okay, that's we good. Now let's come back to the main question. We will use this formula. F inverse prime at 2 equals to 1 over f prime inverse at 2. Okay, now we can see no formula for the inverse again, just this formula. Okay, and now how can we proceed? I will name this quantity x. Okay, that means f inverse at 2 is x. Okay, that we can see I just put x. Then I will put on the side that f inverse at 2 is x, then f of x is 2. Yeah, we know this is the definition of the inverse function. As we can see, I name this quantity x. And now I'm taking care of this. F inverse at 2 is x, then f of x is 2. And what I can do, I can substitute instead of f of x, the formula of the function, which is 1 over x minus 1 is equals to 2. Do you think you can give me the value of x? Can we cross multiply and solve this equation for x? Yeah, who can tell me what's the value of x will satisfy this equation? 3 halves? When we substitute 3 halves, Okay, I am back. I'm just okay. Not oh yeah. Okay, I'm looking at the chat box. Not one, because if we put one minus one is 0. We can't have 0. We can cross multiply 2 times x minus 1, and then 2x equals to 3 halves. And I think I have it. Okay, I can maybe erase this. Okay, 3 halves. That means now I can substitute instead of x 3 halves. Okay, 3 halves, but now we can see what is important. We still have to have derivative of this function, because the final answer will be 1 over the derivative at that value 3 halves. And since we did compute the derivative, proving that the function is 1-to-1, I can use that formula and I can just substitute 3 halves. When we substitute 3 halves minus 1, it will be half. Half squared is 1/4. And then I will flip this, it will be -4. Yeah, that means this quantity is just -4. But I think I have this. And then we can substitute. The final answer is 1 over -4, which of course is -1/4. Okay? That's the way to solve it. But we can see mainly we didn't compute the inverse. We still don't have the formula of the inverse of the original function, but we have the value of the derivative of the inverse at 2. Yeah? Which of course it will be, if we would like to make the interpretation, will be the slope of the tangent of the inverse function at 2. It's -1/4. Okay, let's do another one. Oh, this one is more appropriate because I can show you. Okay, the same thing. Function is defined as 2x plus cosine of x, and we have to find the derivative of the inverse at 1. And now I can show you, because if we will write this function 2x cosine of x, and let's pretend that I would like to find the inverse. I will interchange, y becomes x becomes y, and I have to solve this equation for a new y. Do you think it's easy to solve this type of equation for y? 2y plus cosine of y. How can I isolate y? We have algebraic function, 2y, I mean power function or linear function, and cosine, trigonometric function. How can I pull out that y? How can I isolate y? Yeah, we can see it's not. Yeah, I think it's still possible, because sometimes we can have the situation that is not even possible. That we can see this is the situation that we can't even find the formula for the inverse. Right? But we know that we can skip that step. We don't have to. We can still have the value of the derivative of the inverse at 1 without having the formula. Okay, the same thing. First of all, let's prove that this function is 1-to-1. I think I type it. That means I don't want to show you. What we have to do, who can tell me? How can I prove that this function is 1-to-1? What we need, do you remember? One of the strong tools, we can find the derivative. Yes, that means let's find the derivative, and then I will ask the next question. I can't draw it. Okay, that's when we will find the derivative. And derivative is 2 minus sine of x. And what do you think? This quantity, 2, I mean the expression 2 minus sine of x, it's always positive or always negative? Or maybe sometimes positive, sometimes negative. 2 minus sine of x, it's always positive. Oh, always positive, because what's the maximum and the minimum value? What's the range of the sine function? It's or between 1 and -1. That means when I subtract 1, I have 1. When I subtract -1, yes, that's it's +3. That means because the range is between -1 and 1. This is always positive expression. Which means function is strictly increasing. And I type it. Okay, it's always positive. Okay, that's the good sign. Let's focus on our formula. We're looking for the f inverse prime at 1 equals to 1 over f prime inverse at 1. And we remember, this quantity is 1. This quantity is x. Okay, and now make sure that you understand this. F inverse at 1 is x, then f of x is 1. I'm just interchanging. Okay, instead of f of x, I will substitute my function 2x plus cosine of x equals to 1. Okay, and now we really have to figure out what is the x value. That means this is the moment which is quite similar. Like, do you remember, like I said, it's not easy to get the formula for the inverse because we have to solve for the new y. And this equation is actually similar, or I would say the same. I don't have y, but we have x, and we still have to isolate x on one side. We still have to solve it for x. Yeah? That means in terms of algebra, in terms of solving, it's the same exercise. That's what we will do. We will, of course, not try to solve this algebraically because it's the same. It is possible, but it's challenge. We will not do this. Like, it's the combination of two different type of function. That means at this point, what we have to do, we have to kind of like guess the answer. I know you probably don't like it, but of course we have to make like kind of educated guess. Like, we can think, what value of x will give me actually 1? What value of x on the left-hand side, if I substitute, will give me 1 because 1 is on the right-hand side. And you can always, yes, and I can tell you, if you will reach that moment that you can't solve it algebraically and you will think, oh, my instructor said that I have to guess, you can always try to substitute some numbers, and always the easiest number. Maybe substitute 0, maybe substitute 1, maybe 2, maybe -1, -2. If we have trigonometric function, you may try the radians, like 0, maybe pi over 2. Okay, and I promise one of these numbers will work. Okay, and I see Kevin typed 0. Do you think 0 works? 2 times 0 plus cosine at 0. It is 1? Yeah, what's the value of cosine? Yes, thank you. Thank you for typing. Yes, it is 0. That we can see this will be, okay, that will be the moment that's what we do. Okay, that means this is x is 0. Can you tell me the final answer? Who can tell me the final answer? The only thing that we have to do, we have to get the value of the derivative at 0. And it is, oh, Kevin said 1. What's the final answer? I don't know if I typed here. Oh, can you find the value? No, not undefined. Do you see the derivative here? We have to just substitute 0 because we need value of the derivative. Ooh, 1/3. The last chance. Okay, Noah, we have to be careful. It's 2 or 1/2. Because that value 2 will go to the denominator. Yes, we can see the derivative at 0 is placed in the, okay, that's we have to be really careful. It's this and it's 1/2. Actually, I typed few more steps. Okay, that means please remember, because multiple choice option, yeah, we may have 1/2 and 2. That means please, yeah. Okay, 1/2. Finally, we have the answer. I hope, Kevin, you know your mistake, your error. Because if we can correct ourselves, that's really, yes, yeah, just probably the trigonometric. Good. Okay, let's do one more. Oh, actually, nice multiple choice. Do we have some reciprocals? Okay, no, that's mean I was nice and I didn't give you the mean option. Okay, find f inverse prime at 7 for this function. Okay, and I didn't type the solution. That means what we will do, let's find the derivative because we know we will need the derivative. I can, no, maybe I don't have to rewrite this function as a, because we know what's the derivative of the square root. That means I will compute the derivative, square root. Derivative of the square root, it's 1 over 2 identical square roots. Okay, and times derivative of the inside function, which derivative of inside will be 3x squared plus 2x plus 1. Okay, and I'm assuming that the square root is always positive, okay? And 3x squared plus 2x plus 1 is parabola open up, and actually it's placed above the x-axis. We don't really have to investigate this, but this is definitely always positive. Yeah, with the, yeah, always, doesn't really matter what value of x we will substitute. This is always positive. Of course, if we have with the domain, with the certain domain, because we want the expression under the square root to be positive. But okay, we do have the derivative because we will need the derivative. And it's always positive, strictly increasing function is 1 to 1. Okay, now what we're looking for. F inverse prime at 7 equals to 1 over F prime, F inverse at 7. Okay, and this quantity is x, which means I have to find f prime of x. I have to find this blue x and substitute to this formula. Okay, that's what let's see. F inverse at 7 equals to x, then f of x. Who can tell me what is f of x? 7. Okay, and let's put the function x cubed x squared plus x plus 46 equals to 7. The same situation. We have to kind of guess. We may, for this function, we may do we can apply a few steps, few algebraic steps, or if you know the answer right away, what is the x value, you can tell me. If not, I can maybe do a few steps. I can square both sides, but try. Do you remember what numbers you can try? Yes, I see the correct answer. If I will square both sides, I will have 49. And normally I will subtract 49 and try to solve the cubic polynomial equation. But just because since we're guessing, I can actually subtract 46. That means what value of x will give me 3? Yeah, I see the answer. I think it's 1. That means you did trust your instructor, and I said it will be always 0, maybe 1, -1, 2, -2. Yeah. Occasionally maybe some fractions, but like really basic. Yeah. Okay, 1. Excellent. F prime at 1. Okay. Who can give me the final answer and we can finish our session? F prime at 1. Oh, a little bit of 3 over 7. Let's see, f prime at 1. I think it's the correct answer. I'm just substituting here, okay? I am substituting 1, which will be 3 plus 2 plus 1, okay? 2 times 3 plus 1, oh, not 3, not 3. I'm looking at the 1 cube is not 3. 1 plus 1 plus 1 plus 46. 6, 2, and 49 will, square root of 49 will give me 7. Yeah, 3 over 7, but 3 over 7, luckily, is not the option. What we have to do, we have to place this in the denominator, and then 7 over 3, we have to flip the number. Okay, that means option A is the correct answer. Okay, that means please, I can maybe on this slide, this is the formula from this section and this, yeah, because you can see that's what I'm using. This is our calculus formula and just the inverse notation, inverse definition of the inverse function. Okay, that means this green 2 boxes are the important part. Okay, that's when we can finish. You can definitely do your homework assignments and you will be perfectly fine on your weekly assignments if you understand these. I think I solved 3 questions. I'm just looking. Okay, on the chat box now, I didn't miss anything. Okay, that means thank you very much. And please join me tomorrow. Okay, tomorrow we will talk about the trigonometric inverse. Okay, and we will just focus on the inverse sine function, inverse cosine, and inverse tangent. Okay, we have to know how they look like. We know we can just do them, we can flip them. We have to restrict the domain first, make them 1-to-1, and then make the mirror image with respect to the y equals to x, nice and smooth functions, and differentiate. That means tomorrow session will show us 3 different differentiation formulas. Okay? And for this, for the trigonometric, we will know the formula for the inverse. This one is just general, the general formula. Okay, thank you very much, and please join me tomorrow. Okay, because it's really nice when you attend, when you answering my questions. Okay? And I must say again, I think I'm repeating myself every week. I'm so impressed with your discussion board, with your posts, with using the math editor, math equation editor, like when you answer questions to different students, when you actually ask questions, I really like it. I can see that you grow mathematically, which is so good. Okay, thank you very much, and see you tomorrow at 8 p.m. Thank you.